Hey guys, welcome to your favorite channel, Subhra the Geek. I am your host, I am your host, Subhra. So, guys, as we have seen in the past videos about linear algebra, so today, in the third video of linear algebra of our mathematics series, one of the series which we have planned for you for industry readiness and what the industry wants, along with one of my very good friends, Debayan, who is working in the industry as a core data scientist of past couple of years now, and he's gonna share each and every bit of experience which you need to know. So, guys, how you can use this linear algebra, the concepts of linear algebra we learned in the past two videos in our mathematics series in machine learning, data science, deep learning, and quantum computing. So, today's video will be on that topic. Guys, if you're new to my channel, please hit the subscribe button and hit the bell notification icon beside it so that you get notified each and every time we post a new video and you stay updated with the series which we are pushing on our channel. Guys, please share them with your friend and please share them with all those who will need the content and who wants to be ready for the sexiest job of 21st century according to Harvard Business School. So guys, today we have with me is my good friend Debayan, and guys, we will be helping you out throughout your journey with each and every query which you have via our exclusive Discord server which we have created, and the link is given in the description box below. Please join there, please throw your queries. I and the band will be always there to solve your queries. So guys, I am your host Subhra, and with me is
Debayan.
So without further ado, let's start, shall we?
Hi guys, welcome back. Just to give a quick recap and sort of establish the connecting thread from the previous video that we talked about. In the previous video, we talked about linear systems and how we formulate them using the basic foundational notations of vectors and matrices, and how we use them in terms of matrix computations, matrix multiplications. So one of the prominent equations we sort of pitched in that video is ax equal to b. This equation is it's so prominent, so dominant in linear algebra, and what might call it the soul of linear algebra. Is your intentions are to reduce every problem that you find in real life into an approximation of this expression, and if you solve this expression, you will get an approximation of the solution which can help you solve your real life problem. That was the core insight behind this equation. So if I'm gonna push this equation into a machine learning vocabulary, machine learning kind of terminology, so we have Ax equal to b. So you could say that A is a matrix, X is a vector, and B is your output matrix, right? So in machine learning and data science, we work with data sets. You work with huge amounts of rows with many columns, many variables, and they always have some kind of output vector. They have some kind of output that you want to map your input to. That's what it is. And this data set, you can visualize this data set as a manifestation of this equation Ax equal to b. Every row that you see in your data set, every observation, every row that you see, you have the column on the top, you have the row, so every row can have multiple values for every one of those columns, and then you have an output column which is one value for one row, right? This whole equation is a polynomial equation. If you're thinking as a linear model, if you're starting working with a linear model, so this equation, every row, can be written in the form Ax equal to b, where x vector is the number of variables or parameters or columns that you have in your data set. A is the coefficients or the data numerical values that you see in your data set for your predictor columns, for your actual input columns, and B is just a single value that you see in your output column for that corresponding row that you work with, right? So this is how it physically manifests in your data set. So think of it as if, so for many rows, so thousands and thousands of rows, so every one of those row is one expression of ax equal to b. We have thousands of rows, that implies that these, each one of them is thousands and thousands of manifestations of the same equation, ax equal to b, right? So what you do, or what machine learning engineers tend to do, is to find or somehow condense these equations into one equation, which is of the same form, ax equal to b, such that if you want to use this so-called hypothetical sort of equation, can give you the correct answer, or can at least come give you an answer that's very close to the correct or the expected answer, if you provide in the coefficient values,
Debayan,
right? Hmm?
could you give a real life example regarding this?
Sure. That this is best learned like using a real life example. So I'm gonna give that. So let's think. Consider a human baby, right? Who is learning to identify the shapes of various objects. Right? They're just starting out. They're trying to learn things.
Okay.
That, like, you as a parent or as a teacher or as a
Mm-hmm.
guardian, you're teaching them the shapes of various objects that you see in a room, right? And you bet that they will make mistakes, trying to identify the shape of like a football or ball. They will not understand what the shape of a bottle milk is, like what she's feeding from, or what the shape of a crib where she sleeps is like. Like, she won't understand those kind of shapes. Over time, like, she will learn to see that the shapes of a colorful playing rings is the same as the wheels of the car that she plays with. The shape of the crib is very close to that toy house that she have. They're almost like rectangular box kind of shape. Like, that's the inside that she's forming. And then maybe that the shape of a feeding bottle is very similar to those stands, those cylindrical stands that a crib stands on. She will try to she will see these things, and she will try to make those connections internally in her brain. So what can we learn from this? What can we learn from this process, right? The insight which allows her to learn and store the knowledge about the shapes of all those objects into one compact representation will also thereby allow her to know, or identify, or almost, or you can say, predict the shape of a new object that she sees in the world in the future, right? So if she knows the shape of a bottle of milk, the shape of a cylinder, right? So if she sees something like that, like a lamppost or something, or a bin, like she will see this and say that that's the same shape as that one, right? So you might say, it's still different, right? It's a different object, it's a different purpose, it's not the same thing, but she has learned that there is some property associated with this object that I see right now in front of me that I've not seen before. That's very similar to something that I've seen before, like in the shape of a bottle, milk a bottle, right? So coming back to the mathematical formalism, right? So we would like to find, given the data sets, rows and rows of equations of ax equal to b, the rows that we have, we would like to find out an equation or expression of the same form, ax equal to b, such that, which has, like, where a, right, the input variables will have such a set of values which can approximate any value that we provide, any output value that can provide to it, right? And it will provide a value which is very close to the expected output b, or almost equal to it. Like that's what we want from such an equation. So we don't have to worry about all those maintaining all those equations to understand new unknown kind of equations, new unknown kind of data, right? So we compress that knowledge into that same small equation. We use this equation as our internal model on that same kind of data. So the moment there's a new data comes in as a new row to that database or to the data set, so what you do, if you do not know the output, you pass it through the same ax equal to b equation, right? So it will spit out the value of b given the values of x that we put in, right? and the answer that we get is we can be assured that it's very close to the expected or actual value of b, given that what it has learned from the millions and millions of rows it has seen before, the millions and millions of examples of ax equal to b it has seen before as rows in the same data set, right? So so the terminology is the algorithm which allows us to find this compact representation by finding out those specific set of values for a, such that given a new way, given a new value for x, we can find out the value b very well, at least approximate it very well, right? It's what you would call a statistical learning algorithm, or colloquially known as right now as a machine learning algorithm, right? So this is where the foundation starts, and this is where you sort of try to connect whatever you see is a physical manifestation of that equation, and you just need to make that connection.
So Debayan, thank you for answering all the queries. Like
Hmm.
we now are ahead and understanding how we can connect and use this linear system of equations
Hmm.
for machine learning and data science. Since if
If
we
we learn.
learn this mathematics, we will be moving ahead in our data science series also, and it will be easier
Hmm.
for us to grab those things which you will be sharing with us, if I'm not wrong. But
Hmm. Yeah.
uh, how will this thing help us in our quantum computing series? If you can shower some light on upon that.
Yeah. So so in a similar way, right? So what we're trying to do is sort of make connections, right?
Okay.
So the concept that we learned in linear algebra, the concept of vectors, matrices, and how it works, the operations, we're trying to give them a real meaning, give them a real sense of purpose that we can relate to, we can understand, we can use, and we can learn to use and teach systems to do so as well, right? So in quantum computation, um, I think that one of the basic things that we work with is quantum bits, right? So in classical computing,
Yes.
the ones that
Yes.
you're watching right now, the devices, those are all classical computing devices. So they all use classical bits, which are just contain one of the numbers, 0 or 1, right? In Because they use electricity, it's called on and off. So it's on is 1, off is 0, or vice versa. And you can only store the bits, the classical bits can only store either of them. It's mutually exclusive. So if the bit contains 1, you know
It
that it doesn't
cannot have
contain
zero.
0,
Yeah.
and if it contains 0, you know it doesn't contain 1. That's how classical bits work. So so in qubits, or like that's a short form of quantum bits, you also work with these discrete values, 1 or 0, all right? But you sort of represent them and use them in a different way, just to sort of bring in the concept or lay the foundations of more of using more complex algorithms, and include all the principles of quantum mechanics into this. We're going to talk about that later on in another series, but just for now, just know that we represent the states 0 and 1, as shown on the screen, as 0 will be represented as a column vector with 1 0, and 1 will be represented also as a column vector with 0 1, in that specific order, right? So we represent those states as vectors, as a two-dimensional vectors, or 2 cross 1 matrix, yeah, like if you're following the logic from the previous video. The distinction between quantum computing and classical computing lies in how we store this information, how we store any information using these vectors of zeros and ones, right? In classical computations, we refer to these states as binary states. Just like I said, they're mutually exclusive. So if a state says 0, it cannot be the other one, and vice versa. In quantum computing, a single variable can contain information as parts of the base states, 0 and 1. What I mean by that is, a single variable, the information stored in a single variable, can be expressed as a linear combination of these two states, these two vectors, these two quantum qubit vectors, 0 1 1 0. So they can be interpreted as a single variable consisting of some percentage of information which can be expressed in the zero state, or the zero vector, and some percentage of information in the one state, and you combine them in those specific percentage ratios. That is a linear combination of two base vectors, and when you add them, the final state that you get is a quantum state. That's your quantum information, and then you perform all kinds of operations on it, which is very very similar to the ones that we defined like in our previous video on matrix computations, matrix multiplications with vectors and matrices.
So what Debayan is saying is like a classical bit. If we have a classical bit, it can
Mm.
have a possibility of two values, storing two values. But in quantum or qubits, it has a possibility of storing 2 to the power n values. You may say
Mm.
how. So how is like in a classical bit, as the Debayan correctly mentioned, is it can store either of 0 or 1. So if we want to represent a 3-bit number, we will need 3 individual bits. But in quantum, if we have 3 bits, we can store all the possible values, all the possible 8 values, binary values which we know, using those 3 bits until and unless it is measured. This is the quantum superposition, and by this phenomenon, the quantum bits store these values. So this is the advantage which quantum has over classical computers. So that's the thing, and that is nothing but, as Deban mentioned, and thank you Deban for mentioning, it is a linear combination of those values which we use to represent any state in quantum. Since it can have any of the probability of having 0 and 1. If we combine them, we can get a unique state, and each combination will give us a unique state. Thus, quantum can store much more information than classical bits, and that is the quantum advantage. And
Yeah,
the
Subhra, I want to interject over here just so that the audience can sort of get a very clear understanding.
yeah,
So the way that we get that power of thing, that power exponential power thing, right?
yeah,
So in classical bits, you have 3 bits.
yeah,
That's all you can store. You can just store 0, 1, 1,
exactly,
1, 0, 0. Yeah. But in quantum bits, if you have 3 quantum bits,
yeah,
what it implies is that in just one bit,
yeah,
you can store an almost infinite combination,
yeah, exactly,
effectively infinite combination of zeros and ones in some percentage vectors together.
yeah,
This linear combination is what we call like is we call an aspect of superposition,
yeah,
right? And think of 3 bits having these superpositions at the same time. You are effectively denoting a large like an exponential amount of information in just 3 bits, right? You don't need 100, you don't need like thousands and thousands of bits to represent the same information. In fact, one of the top like the most commercially available quantum computers in Rigetti or Forest SDK or IBM, what can offer is they only contain 50 or 100 bits at most if they can maintain it,
yeah,
right?
exactly.
And
Like
yeah.
Jay Gambetta of IBM recently shared a post via his Twitter where he claimed that IBM Montilev, if I'm not wrong, has a quantum volume of 128. That's a maximum which has been achieved till date, and it is shared just a few days back, like in on 2nd or 3rd of December. So
Mm.
that's the maximum, and for those 128 bits, we can store, like as Devan said, a humongous amount of data.
We can easily store all the YouTube videos.
Yeah,
I think we can. Yeah. Like it will still have space. It will still have space
yeah,
for another like thousands of years of YouTube videos. It's that much amount of data, right? That's the power. That's where the whole craze and hype about quantum computing comes into play, and that is why we will be exclusively working on this YouTube series as well on quantum computing.
and Devan will be surely discussing about how we saw this exponential power while we were solving those challenges. One of our challenges, do you remember?
Yeah.
This
So
exponential power where we
uh,
stored. We will be
yeah. So
sharing it in
yeah,
that
we'll
series.
be
Yeah,
sharing. Yeah.
yeah. Not now. Let us give us a hint to them that we will be sharing. So they should stay tuned.
Yeah.
So
Definitely stay tuned. Yeah.
so guys, that's all for the day. Thank you, Devan. So that's all for the. Thank you guys for staying with us for so long. Uh, till next time, I will be discussing few more concepts of mathematics. So we'll see you guys on the next week's video. So I am your host Subhra, and with me is
Debayan.
we are signing off. Bye bye. Thank you.